what we're going to do today is we're going to talk about yet another form of synchronization mechanism in Java util.concurrent. And this one is called the condition object. It's actually in Java util.concurrent locks. And what we're going to do is we're going to talk about how these condition objects enable user-defined Java objects to have multiple wait sets per object. Does anybody know what a wait set is? It's sort of self-explanatory at some level. What do you think you can do with a wait set?
Wait for something.
You can wait for something, right? Surprise, surprise. You can wait for something. And where have you encountered something along the lines of a wait set heretofore?
Blocking queues.
Blocking queues, right? Like blocking queues, good. What other thing? What?
In the monitor object.
The monitor objects, right? Monitor objects have a wait set, right? They have one. But as we'll see, there's often circumstances where you'd like to have more than one. So we're going to see how condition objects allow you to have Java objects that have more than one wait set, because they already have one, which is their condition, their monitor condition, or their wait queue, as it's often called. But this is going to allow us to have arbitrary numbers of them. So a condition variable is conceptually a queue of threads where a thread may wait for a condition to become true. That's the basic thing that a condition gives you. It's a way for you to wait. That's why it's called a wait set. And if you take a look, there's some discussion about so-called condition variables. We're talking first about the concept of conditions before we talk about Java's implementation. We're talking about the concept in general. They're often used in situations where mutual exclusion alone is insufficient. Why would mutual exclusion be insufficient? What would be a condition under which it would be insufficient? What class of problem are not solved by mutual exclusion?
When you need it to be coordinated as well.
When you need it to be coordinated as well, exactly. So you have a situation where, busy waiting or even sleeping is not enough. You need to be able to put yourself to sleep until something changes that's to your liking. And a mutex or a reentrant lock or a reentrant read-write lock or even a semaphore doesn't really give you that capability. And there's a whole discussion of this issue here in this link. So when you need condition variables, what you really are doing is you're implementing something called the guarded suspension pattern. And that's described here at this Wikipedia article. It's worth reading it. And it also appears in a book I wrote a couple years ago. And basically, here's how it works. So you have some piece of code, and you need to do something, right? You're trying to get something done. So you acquire a lock, and then you check to see if the condition you're waiting for is satisfied. What would be an example of a condition we might want to wait for? Can we think of a good example based on things we've done?
Permits greater than 0.
What's that?
Permits.
Permits greater than 0. There you go. That's a good one. Or, queue not empty or queue not full, or all these things like that. So while the condition is not satisfied, of course, you're going to loop. But once the condition is satisfied, you're going to go ahead and do some work. So that's why it's a guarded suspension. You're guarding this thing from running until the condition is what it wants. When it can't make progress, in other words, when the condition is not satisfied, then it goes to sleep on the condition variable. And this will wait until the shared state, which is really what this thing is accessing and checking, until some shared state or mutable state may be true. Remember, there's always this sort of conditional nature to this, right? It might be true. Maybe it's not true. We'll come back to that in a second. Now, remember, so you're waiting till the condition becomes true, and the condition becomes true when some other thread makes a change to that mutable state and signals the condition variable, which will then cause this thing to wake up again, and now it can go ahead and check the condition, and assuming the condition is satisfied, it can make progress. Now, here's a couple things to keep in mind. These conditions, it doesn't really show it here, but in real life, the condition can be some arbitrarily complicated thing. It could be, while count's greater than 0, and queue is not empty, and the cow jumped over the moon, whatever. It could be a bunch of different things that might be happening. And because it's arbitrarily complex and it involves shared state, which is always the kicker in the concurrent programs, there needs to be a lock that's associated with the condition variable to protect the state that's shared between the threads. And of course, the rule is you can only access and read or write to that shared state when the lock is held. That's an example of an invariant. When the lock is released, the invariant must be true. While the lock is held, you can be mucking around with stuff and changing things. But by the time you release that lock, the invariance must be restored. So you have to lock the lock, and then you await. And when you wait on a condition when the lock is locked, that atomically releases the lock and suspends the thread. Those two things have to happen at the same time. If they don't, bad things will occur. Now, mercifully, that's not your problem. That's the condition variable implementer's problem. And assuming they get it right, then you're in good shape. So when you release the stuff, when you do the await, the lock is unlocked as you go to sleep. So now you're asleep, snoozing away. The other thread comes along. It acquires the lock, which you released, right? If it didn't release the lock, you couldn't acquire it. The other thread couldn't acquire it, which is the whole thing we talked about in the specific notification pattern. That's why you couldn't hold the lock on this across upcalls or callbacks to manipulate the wait on the specific notification. And this guy will then signal the thread. He wakes back up again and checks the condition and does his thing, assuming he's the one who's able to run. And we'll talk more about that later. So that's one way to look at this. There's a whole bunch of different ways to visualize the interactions between threads and objects in the condition object or condition variable way of doing things. And we're going to show a bunch of different views. Why are we going to show a bunch of different views? Because it takes a while to sink in. It's not easy. In fact, this is really what makes this subtle, right? It's those interactions. That's the whole coordination aspect. We're coordinating the ordering in which things run. We're not just locking stuff out. So I always like to remember the differences in my mind as follows. Things like mutexes or synchronized blocks or even reader-writers locks, they are used to keep others at bay while you do your thing inside a critical section. That's the purpose of those locks. Conditions are a little different. They're more to put yourself at bay or keep yourself at bay while the world or the state of the world isn't to your liking. And then when the world may be back to your liking, when the state of the world may be back to your liking, someone else coordinates with you cooperatively to wake you up so you can recheck to see if you can make progress. So it's kind of a different slant on things. All right. So that's the guarded suspension pattern in a nutshell. Condition variables and their realization as condition objects form the basis for higher level synchronization mechanisms in Java. For example, blocking decks and queues use these things because they're implementing the producer-consumer problem with a bounded buffer, right? That's how you would typically use them. So you don't access the condition variables directly. You see them behind higher level operations like put and take, for example. And of course, this is all implemented by the condition object in the abstract queued synchronizer, abstract queued long synchronizer, and so on. And we'll come back later and we'll look at ArrayBlockingQueue as an example of one use of condition variables / condition objects. We'll also come back probably much later in the course if we have time, and we'll look at the monitor object pattern. And then we're going to look at an even cooler implementation of linked blocking queue. So ArrayBlockingQueue, as you'll see in a minute, uses an array as the backing store for the data. Linked blocking queue uses a linked list. And it does some really cool things because what it does is it actually has 2 reentrant locks per linked blocking queue. And it uses 2 of them, so it's possible to add and remove items at the beginning and end of the queue concurrently to each other, which is an even more super-duper optimized way of enhancing concurrency control. And you can take a look here. We'll talk more about this. We'll look at the implementation in a minute. Of course, Java built-in monitor objects also are examples of condition variables. They're called wait queues and stuff like that. And that implements the monitor object pattern, which we'll talk about later. The thing to remember is condition variables are very powerful, but they're hard to understand and apply. There's several reasons for that. One reason why they're hard to understand and apply is you have to keep track of the association between the lock and the condition. And you have to remember that they're related to each other in various ways. That's important. Secondly, there's obviously relationships going on between different threads that have to be coordinated with each other, and that takes a while to get your head around. Plus, there's this murky issue of the condition that you're waiting on. How do you do that? So as a consequence, they're usually hidden within other abstractions. So you very rarely access them directly. You don't usually use condition objects or condition variables in your application code. It's almost always hidden beneath a monitor object interface or a producer-consumer interface and so on. And in fact, as we'll see when you look at Android, that's really the way it is. There's almost no uses of condition objects anywhere except in the libraries that provide the higher level abstractions for concurrency control. All right, human known use of condition variables. So keep in mind what we've talked about. We use the restroom protocol in an airplane as our example for reentrant locks. We used updating the Vanderbilt website content for readers, writer locks. We used playing beach volleyball in Corona del Mar as our example for counting semaphores. Now we're going to look at a fun, somewhat whimsical example of condition variables. So let's say that you decide that in your spare time you're going to get some extra money by working in pizza delivery. Because let's face it, this software stuff, it's probably a flash in the pan. Okay, but one thing endures: delivering pizza. It's always a growth industry. When people are happy, they eat pizza. When people are sad, they eat pizza. Right? It's like Bud Light or something like that, or vodka. People love it, so they're always going to use it. So what you do is you go to the pizza place, like Papa John's or whatever, with a bunch of your friends who are all going to work together with you. And there's a protocol that you have to follow. So the way things are going to work is that when a pizza is ready for delivery, you have to get both the keys to the pizza truck and the pizza in order to be able to deliver the pizza to whoever it goes to. So you need two pieces of information. And because you're working as a second or third job, when you're not delivering pizzas, you're going to sleep. Okay, so you're going to, and there's a bunch of your friends there that are kind of hanging out, dozing and watching reality TV shows or whatever and sleeping. So when the cook has finished cooking a pizza, the cook puts the pizza in a little, like a little table or something like that, and rings a bell. And when the cook rings the bell, all the waiting pizza delivery people wake up, and they have to do two things. They have to contend to get the pizza, because there's a bunch of them, and they also have to contend to get the key to the delivery vehicle to drive. For some strange reason, let's say that there are more people than there are delivery vehicles. I don't know why. Maybe times are tough, Papa John's. So the rule is when you come back from delivering a pizza, you put the keys on a hook and you ring a bell, and that causes everybody to wake up. And when the cook is done with the pizza, the cook puts the pizza out, rings a bell. So a bell is being rung under two conditions. You're releasing keys and you're creating pizzas. When that happens, everybody has to go and try to grab the stuff. So in order to make progress, you've got to get both items, the keys and the pizza. Now here's a couple questions for you. In what order should you acquire those resources, or try to acquire those resources? Should one group of people try to grab the pizza first and then the keys, and the other group of pizza try to grab the keys first and then the pizza?
Probably not.
What would happen?
One group gets keys, one group gets pizza, and nobody does anything.
And what's that called? Deadlock, right. So ordering, making sure that you try to acquire the resources in a consistent order is very important when you're doing this kind of stuff. That's another thing that makes this complicated, right, is remembering this. Now, for something as simple as this example, it's not too hard to remember. Always try to grab the pizza first, followed by the keys. But imagine a much more complicated program with lots of shared state and lots of conditions that are being waited upon. It gets complicated in a hurry. So the rule is that you have to get both of those resources. And if you are able to get one but not the other, you have to release what you got and go back to sleep. So if you can't get the pizza and the keys, then you have to go back to sleep again. So keeping that metaphor in mind, that gives you a pretty good human known use for condition objects. All right, so let's talk about how these things actually work in Java. The condition object provides the condition variable abstraction. And as you can see here, the condition object is a class. It's part of the abstract queued synchronizer. It implements the condition interface, which is described down here. And under the hood, the abstract queued synchronizer.java file is where the condition object actually resides, which is down here. So you can go look at the source code if you want to. Not surprisingly, under the hood, condition objects are implemented by queues of waiters. And that's one of the things that abstract queued synchronizer does very well. It lets things wait using variants of the specific notification pattern. Now, keep in mind, again, you can control, as we'll see in a second, whether condition variables are fair or non-fair. There's also some other curious thing that Android provides called a condition variable, which is not quite the same thing as a condition object. We're going to ignore it, but it exists, so don't get confused. So the key methods, surprise, surprise, in a condition object basically focus on waiting and notifying. So here are some of the methods: await, signal, and signal all. Well, gosh, that looks strangely familiar, doesn't it? That looks like Java's built-in monitor object methods, except those are called wait and notify all, whereas here they're called await, signal, and signal all. Go figure. I don't know why they changed them. I guess they didn't want to confuse people any more than they were already going to be confused. There's a bunch of different kinds of wait methods defined. So here's one that will wait until the current thread is signaled or interrupted. Then there's also this one called await uninterruptibly. Remember how I told you that there was a little confusion going on when they did this stuff? So Rantrant lock has lock and lock interruptibly. So that implies lock is not interruptible. Condition object has await and await uninterruptibly, which implies that await is interruptible. So a little backwards, a little confusing. You can wait in nanoseconds. You can wait in, I think it's milliseconds. And then there's also this await until thing. So there's a bunch of different ways to wait. Internally, as I mentioned before, there's a whole pile of queues that are used to keep track of all this stuff. We're not going to talk about that, but that's all in queued, abstract queued synchronizer. Now, here's another thing to remember. This is a little confusing. This is also the way it works with monitor objects, but you don't see this because it's done for you implicitly, unless you do it wrong. When you use a Java condition object, you have to associate it with a lock. Now, this turns out to be very easy, as we'll see in a second. Likewise, when you use a monitor object, that is also associated with a lock. And in the case of a monitor object, it's associated with the intrinsic lock that is this. And so, of course, you have to make sure that when you call wait or notify all on a monitor object, that the this lock is held, either because it was a synchronized method or you're in a synchronized block. If you don't do that properly, you'll get an illegal monitor state exception. So we have a lock that goes along with our condition objects. And fortunately, there's a method on lock called newCondition. NewCondition is a factory method that returns to the caller a condition object that is associated with that lock. And under the hood, of course, it's a condition object. It's returned as a condition using the condition interface. So you get back a condition. It doesn't expose the fact it's a condition object to you, but it is under the hood. And you can take a look at this link to find out more about that method. Now, here's where things start to get different from monitor objects. So monitor object, remember, they just have one monitor condition or wait queue. User-defined objects can have as many condition objects as they want. It's totally up to them as to how many they define and how they use them, unlike built-in monitor objects. All right. So that's basically the condition object. The interface itself is pretty straightforward, except for there's a lot of await methods. It's the usage patterns that get tricky. So what we're going to do next is we're going to take a very detailed look at an example to illustrate the proper use of condition objects in Java. To make the discussion very concrete, we're going to look at the way in which the ArrayBlockingQueue class is implemented. Now, ArrayBlockingQueue is part of java.util.concurrent. It's one of the bounded blocking queues that are there. There's several of them. I think there's synchronized blocking queue, there's linked blocking queue, and there's array blocking queue. There may be a couple more blocking queues nestled in there somewhere, but those are the key ones. Linked blocking queue and array blocking queue. As you might expect, an array blocking queue is a blocking queue backed by an array. So it's implemented as an array. And of course, the array can grow if you want to grow it, and so on and so forth. ArrayBlockingQueue extends the abstract queue class, so it implements a bunch of methods from that, and it implements the blocking queue class. As a consequence, it's rather complicated. There's a lot of methods. In fact, I was listening to Doug Lee's great YouTube video the other day about about engineering concurrent library components. And he makes the case, or he makes the point, that most people use bounded blocking queues to put and take. That's all they do. They put something at the end. They take something off the front. That's about all they do. And he said, 90% of the complexity in the implementation was figuring out how to do a take or a remove from somewhere other than the beginning or the end. That's where all the complexity goes, which is a use case that's not really very common. You don't typically use a concurrent queue for anything other than putting things at the end, taking things out the front. Or maybe sometimes you'll put things at the front too. But the point is that removing stuff from the middle is very uncommon, but that's where all the complexity goes. So I thought that was kind of an interesting observation. So these things are also sort of Java collections in some ways as well. Here's the source code. That's what we're going to look at. We're just going to look at some of it, not all of it. We're going to look at the stuff, surprise, surprise, that relates to condition objects. We have previously looked at the code that related to acquiring and releasing reentrant locks. So we're not going to spend much time on that. That was covered in the earlier video. OK, so under the hood, there is a dynamically sized array called items. And then there's also a few other things, the take index and the put index, which keeps track of where you put things into the queue. If you took 251 with me, and maybe if you took 251 in general, there was an implementation of a couple queues. Remember, we had a linked queue and an array queue and so on. These are sort of along the same lines as that. You keep track of where the puts and takes go by using indices into an object array. And then it's got the synchronization objects that are used to guard the state of the queue. So it's got a reentrant lock, reentrant lock, of course, and it's got two condition objects. And here's the thing that's kind of funky. Both of these condition objects share the same reentrant lock, and that's actually very important. One of the more powerful and cool things about condition objects or condition variables in general is the fact that they can share a common lock. So let's take a look at the constructor. Here's the constructor for ArrayBlockingQueue. You give it how big you want the queue to be, and you give it whether you want it to be fair or not. And you come in here, and you'll notice that it creates a new array of that many items. It makes a new reentrant lock that's either fair or non-fair. And then you go ahead and create a pair of conditions using the factory method on the lock. So you make not empty and not full. So at that point, that's what you have in your state. A lock, reentrant lock, a not empty condition variable, a not full condition variable, and some state. Now, judging solely by the name, what do you think not empty and not full are going to be used to guard? What's their purpose in life? Underflow and overflow, right? So when the queue is empty, you're going to use the guarded suspension pattern to wait until the queue is not empty. And when the queue is full, when it's reached its capacity, you're going to go ahead and use it to wait for the queue to be not full. So those are the boundary conditions. Now, an awful lot of the time, depending, of course, on a variety of factors like how many threads there are, adding and removing stuff, how fast those things run, etc., you might be in steady state. And so if the queue is not empty or full very much, if it's got stuff in it most of the time, these condition objects will be used rarely. But when they are used, they're needed because you don't want to sit there and spin, or worse yet, just bomb out if you reach a boundary case. Let's take a look now at how we might use this stuff. So this is going to implement the so-called monitor object pattern. I'll show you a picture alongside the code. You will have to decide whether it's easier to understand the picture or the code. It may be distracting to look at both, but let's give it a shot. So here's what we got. We got lock, not empty, not full. We have the lock, which is what guards access into the waiting room, if you will, for the condition object. This is actually the array blocking queue, this whole thing. This is the lock that gets you into the critical section. And then we have two sort of anti-rooms, which are not full and not empty. If you recall our little drawing of the hospital waiting room that we used before when we first talked about monitor objects and notifies and stuff, that's kind of the same idea. All right, so let's assume we have thread T1 that comes along and calls take on a queue with no items in it. So the queue is empty. But we have a queue that can hold up to 10 items. So here's what take does. We come in, and take is called, so we sort of get into the reception area. We then go ahead and try to lock interruptibly. So assuming that works, assuming we're the first one in here, we get ourselves into the critical section. And now we're in the critical section. And now we're going to run the stuff. And at this point, no other thread can be in here. Why can no other thread be in here? We got the lock, right? Lock is held. So while the count is equal to 0, which it will because it starts out at 0, we need to go ahead and wait. When we wait, remember what happens. We release the lock, and we go to sleep off in this little side room over here. So now we're going to be blocked on this condition object. We're blocked on the not empty condition object. All right, now let's switch gears. So this guy's blocked in one thread. Now thread T2 comes along, and he's going to go ahead and put something into the queue. So when put gets called, he gets into this little waiting reception area. He can acquire the lock because it was released before, right? And now, while the queue is not full, right? So while count is less than items length, if it was equal to items length, then we would have to go ahead and wait. But of course, it's empty at this point, so it's not going to wait. So what he does is he goes ahead and calls insert. Insert gets called, and insert puts the item into the queue at the put index and increments the put index, just like your program from 251, if you remember back whenever you took it, if you did that assignment. Remember, increment wraps around, so it does like a circular queue. Same idea. We increment the count by 1, and then we go ahead and we signal. So signal, of course, is going to be this guy's job to tell this waiting thread, you can now wake up again and see if the queue is no longer empty. When signal gets called, that guy will be in a position to run. And when, let's see. And then as we leave here, so this was insert. So there we go back here. Lock.unlock is now called. That releases the lock. And now we're going to be able to let this guy wake up. So this guy is now gone. He leaves the monitor. And now we come back around here. This guy's sleeping, or had been sleeping, on not empty. Now he's just been awakened by the signal that occurred back here. And now he's going to wake up with reacquire the lock. That gets done. You don't return from await until the lock has been reacquired. And now with the lock held and you be awakened, you can now come back and check to see if count is 0. Why do we have to check if count is 0?
There might have been more people in not empty, or just somebody who came along later.
Someone may have come blazing along for whatever reason between the point when we were awakened and the point when we had a chance to try to grab that, to grab the lock and check. It could have come along and removed a message. So we're sitting there like, oh, darn, we woke up, and now we have to go back to sleep again. That's just like the scenario I gave you with the pizza, right? You heard the bell, you woke up, you stumbled forward in a daze because you were half asleep, tried to grab the keys, someone had already got them. You're like, oh, darn, I'll go back to sleep. So that's basically the idea. OK, assuming that we do, in fact, have an item in the queue, it's not empty, we then call extract. Extract does some stuff to remove stuff, and it updates the index, decrements the count, and then it goes ahead and it signals the not full condition. Now, in this particular case, there was nobody waiting for the queue not to be full, right? That wasn't being done at the moment. Had there been, and had we just taken something out, we are obliged to inform them that they should wake up. Now, there's all kinds of other subtle optimizations you could do. You could do stuff here where you wouldn't signal unless you knew you had a waiter and all that kind of stuff. That can sometimes get so complicated it's not really worth doing. Calling a signal and nobody's there to wait isn't a problem. It just, nothing will happen as a result of it. Calling a signal when there's no waiters does not leave any trace. The next guy who comes along after a signal's been called will not find the signal to have been set. Any state that you want to have that has memory or history associated with it, you have to do yourself. OK, so we come back, we get the result, we return it, and the final thing we do on the way out is we unlock the lock, and we go ahead and leave the monitor. OK, any questions about that? So this is one of those things where you can think you understand this, and until you sit down and actually try to write it and do something other than something as simple. This is a pretty simple example. It gets kind of subtle. This is also why people typically like to hide this kind of stuff in higher level abstractions, like bounded queues or bounded buffers or monitor objects or something. Putting that stuff inside of some other abstraction, so you do things like put, take, right? Put and take, that's pretty easy to get your head around. This kind of stuff is too low level for most people, so that's why they typically like to see it hidden under higher level abstraction, because it's easier to work with. OK. Now, there's a bunch of usage considerations that you need to keep in mind when you're applying condition objects. And what's interesting is that the usage considerations are actually a little bit more complicated than they were for some of the other stuff. I mean, let's face it, reentrant read write lock, reentrant lock, pretty darn easy, right? Synchronized keyword, pretty darn easy. There's only so many things you can do to get it wrong. With a reentrant lock, you can forget to unlock it. With a synchronized block, you can't forget to unlock it, right? You can do other things to screw it up, but you're not going to forget to unlock it because it happens automatically. So the first thing to remember is that condition objects are very, very flexible. They give you, great power. But what did Peter Parker's uncle always tell him? Right? Great power comes great responsibility. So you have to make sure that you're using these things wisely. The things that you can do that are cool is they allow threads to suspend and resume their execution. And I mean that in a broad sense. You can suspend yourself, and then you can resume somebody else, right? So that's kind of the way it works. At a lower level, that's known as park and unpark. But at the level we're working here, it's basically wait and signal all. So that's one thing you can do. Objects can have multiple condition objects. This is really cool. This is what sets us apart from just plain old Java monitor objects. We can have multiple of these things. And it's instructive, if you're so inclined, to take a look at the ArrayBlockingQueue implementation and then go back and compare and contrast it with our earlier implementation. I think we called it Simple Blocking Queue. The Simple Blocking Queue implementation, which appeared earlier in the course, used a monitor object. So if you go back and watch the monitor object videos, we used Simple Blocking Queue. And Simple Blocking Queue just used wait and notify all and stuff like that. And it had to wake everything up, because there was only one condition object. And so it actually looks easier at one level, but it's way more inefficient than using condition objects. You always use them in conjunction with a lock. That goes without saying. When we talk about the next assignment number 3, you'll see that it's got some really cool stuff in it. And I'll show you a bunch of other ways to do it above and beyond what you're going to be doing. But one of the things you can do is you can use condition variables to have two threads play ping pong with each other. And it's really cool. It's kind of funky. And we'll look at it. But it relies on the fact that the condition object can share a common lock. Here's an important thing. You should always, or just about always, wait for these things in a loop. There are rare occasions where that's not the case, but it's almost always the case. And the reason for that is that you need to be able to check the state that's being waited on to make sure it actually fulfills your needs. The world is the way you want it to be. And if you read here, you'll learn more about why that is. And the other thing you've got to watch out for, and this is a really subtle one, is something called spurious wake-ups. And if you take a look, you can read about spurious wake-ups here. Basically, a spurious wake-up occurs in a multiprocessor, often occurs in multiprocessor environments, where for efficiency's sake, you need to notify a bunch of things even though only one thing has occurred. And the reason it works, it's often done as a way to optimize the performance in a hardware environment. And so the hardware people are always making their lives easier, assuming that us software people will clean up the mess that they make. And that's sort of a short history of hardware for the past, I don't know, 50 years. And then they blame the software guys for having to deal with complexity. A friend of mine once said, blaming software for being complicated is like blaming a vacuum cleaner for being dirty, right? That's what it's there for. It's there to clean up the mess, right? So that's kind of what software, at least systems software, is there for. It's there to clean up the mess that the hardware people make. So spurious wake-ups, if you're awakened for reasons having nothing whatsoever to do with the fact that somebody notified you, basically a spurious wake-up occurs when someone calls notify, but it acts something like a notify all, which can happen. And if you read this article, you'll find out why. Condition object is used relatively sparingly in Android, and I should say, in higher level things, right? Android being an example of a higher level thing. Where it is used in Android is lurking in java.util.concurrent and java.util.concurrent locks. There are examples in there. In fact, we'll look at that in a second. And of course, it's used indirectly in Android's concurrency frameworks, which we're going to cover later in the course once you get done with the Java stuff. By the way, one of the interesting things, I was kind of thinking about this the other day, I was like, when we learn about Java concurrency, synchronization is a big deal, right? For the most part, especially at the level that we've been talking so far, where we've just sort of learned about threads. So we've learned about all these different locking mechanisms and so on. When you get to Android concurrency and the concurrency frameworks, there's just about no synchronization to be found. All this stuff just sort of disappears. The reason is because these higher level frameworks are protecting you or guarding you from the need to know a lot of this lower level stuff. So here's a question for you. What would be the circumstances under which you would prefer to use the sanitized for your protection higher level framework approach to concurrency versus the you need to understand how it works under the hood purpose? What would be some different reasons for doing one versus the other?
If you want a better performance.
So performance is a big deal, right? So the higher level abstractions are great as long as you're not worried about the fact that they incur additional overhead. And why do they incur additional overhead? What's the reason why these higher level abstractions may, not always, sometimes they actually are great, but other times they incur higher overhead? What's the reason for that?
They probably need to be overly safe because they're making the framework for general use cases.
That's right. They're trying to cover a general purpose thing, and we're often doing more special purpose things. And so if they're optimizing for the common case, and if you're not in the common case, then and the non-common case matters, right? It actually has some impact on quality of service or user experience or reliability or throughput or whatever you care about. Then it helps to know the lower level stuff. It also might be the case that some people will here might go to work actually for an infrastructure provider. So you might go work for the Java VM team or the Android Art team or their Dalvik team or something. So then it would be important to know these lower level things. And of course, it's also just useful to know how things work in general. The buzzword of these days is called full stack programmer. That's what some people aspire to because they can know things from top to bottom.